The topic of presentation is about axial load. Also, we will discuss on St. Venant's principle, elastic deformation of an axially loaded, statically indeterminate axially loaded member, and the force method of analysis for axially loaded members. Explanation of axial load. The strength of a material can be known with the help of axial load. The axial load of an object is responsible for the force which passes through the center of the object, is parallel to its axis of rotation, and perpendicular to the plane of cross-section. The force owing to the axial load acts on the central axis of the object, and it can be a compressing or stretching force. The central axis, or the axis of rotation of an object, is that axis around which the object can spin. Axial load is also known as thrust load. Axial load calculation. The formula to calculate the stress due to axial load is.
This is St. Venant's principle. It states that the difference between the effects of two different but statically equivalent loads becomes very small at sufficiently large distances from the load application. For example, if we have a concentrated force acting on a beam, there will be high stress right at the point of contact. But as we move away from that point, the stress distribution will become more uniform, and it will be less and less affected by the exact shape or size of the load. This means that the intense localized stress spreads out and smooths over a short distance. As a result, far from the load, the structure's response depends mainly on the total load, not on how it is applied. Specifically, it depends on the force and the moment, not the way it was applied. This is St. Venant's principle. As for example, Tutorial 1. 2 steel rods, each 1 meter long and 30 millimeters in diameter, are loaded axially at one end. Rod A, the load is applied uniformly across the entire cross-section. Rod B, the same total load is applied through a small circular plate at the center of the cross-section. Explain, using St. Venant's principle, whether the stress distribution will be the same along the rods. The answer: according to St. Venant's principle, the difference in stress distribution caused by the two different load applications will be significant only in the immediate vicinity of the loaded end. Beyond a distance roughly equal to the rod's diameter, approximately equals 30 millimeters. From the loaded end, the stress distribution along both rods will be nearly identical, because the total resultant force and moment are the same in both cases. Example tutorial number 2. A solid steel rod, diameter D equals 30 millimeters, is loaded axially with P equals 90 kilonewtons. Compare the axial stress at a section far from the loaded end, say at 200 millimeters from the end. For two loading methods, A, the load applied uniformly over the entire cross-section, and B, the same total load applied through a small central pad concentrated over a tiny area. Use St. Venant's principle to state the stress value far from the load and compute it. The answer? Conclusion. At 200 millimeters from the loaded end, axial stress is essentially identical for A and B, and is equal to 127.31 megapascal.
Elastic deformation of an axially loaded member. In engineering, the deformation of a body is specified using the concepts of normal and shear strain. Whenever a force is applied to a body, it will tend to change the body's shape. These changes are referred to as deformation, and they may be highly visible or practically unnoticeable. Deformation of a body can also occur when the temperature of the body is changed. The figure shows the before and after positions of 3 different line segments on this rubber membrane, which is subjected to tension. The vertical line is lengthened, the horizontal line is shortened, and the inclined line changes its length and rotates. Elastic deformation is the temporary change in the length of a structural member when subjected to an axial load, either in tension or compression, within the elastic limit of the material. When the load is removed, the member returns to its original length without any permanent deformation. This concept is based on Hooke's law, which states that stress is directly proportional to strain within the elastic range. To generalize the development off the formula, let us consider the figure below. The axial load, Px, deforms the element, causing a small displacement deltad between its ends, with stress and strain developed in the material. For the entire length of L of the bar, we must integrate this expression to find the required end displacement. Provided that these quantities do not exceed the proportional limit, we can relate them by using the Hooke's law. Analysis of elastic deformation in axially loaded members. Determine cross-sectional area. Applying the elastic deformation formula, considering tension versus compression, material property influence, and multiple segments. Example 1. A member made from a material that has a specific weight and modulus of elasticity E. If it formed into a cone having the dimensions shown in figure, determine how far its end is displaced due to gravity when it is suspended in vertical position. The solution is: the internal axial force changes along the member because it depends on the weight of the segment below each section. The cone's radius at distance y from the bottom is determined proportionally to its height. The volume of a cone having a base of radius x and height y is. Since W-WFO, the internal force at the section becomes. The area of the cross-section is also a function of position y as shown in figure B, and therefore, applying the equation above. Tutorial 1. A homogeneous cylindrical rod has a length L 1.5 ml, radius arbor 10 ml, specific weight Gr 78.5 kN m3, and modulus of elasticity E per 200 GPa. Determine the elongation of the rod due to its own weight when suspended vertically. Tutorial 2. A solid cone-shaped rod with a length L bar 2 ml has a radius at the top arb 30 mm and tapers to 0 radius at the bottom end. The material has a specific weight, Gr 27 kN-m3, and modulus of elasticity, E70 GPa. Determine the elongation due to its own weight when suspended vertically with the pointed end down. Statically indeterminate, axially loaded member. Static indeterminacy does not imply that the problem cannot be solved. It simply means that the solution cannot be obtained from the equilibrium equations alone. A statically indeterminate problem always has geometric restrictions imposed on its deformation. We can, however, use Hooke's law to express the deformation measures in terms of stresses or forces. The equations of equilibrium and compatibility can then be solved for the unknown forces. This type of problem is called statically indeterminate, since the equilibrium equations are not sufficient to determine the two reactions on the bar. In order to establish an additional equation needed for solution, it is necessary to consider how points on the bar displace. Specifically, an equation that specifies the conditions for displacement is referred to as a compatibility or kinematic condition. In this case, a suitable compatibility condition would require the displacement of one end of the bar with respect to the other end to be equal to 0, since the end supports are fixed. Hence, the compatibility condition becomes delta AB over 0. This equation can be expressed in terms of the applied loads by using a load-displacement relationship, which depends on the material behavior. For example, if linear elastic behavior occurs, PLAE can be used. Realizing that the internal force in segment AC is plus FA, and in segment CB, the internal force is FA. The above equation can be written as, assuming that AE is constant. Example 1, solution. Example 2, solution. Example 3, solution. Example 4, solution.
The force method of analysis for axially loaded members. The force method, also called the method of consistent deformations, is a structural analysis technique used when a structure is statically indeterminate. A statically indeterminate structure has more unknown forces support reactions or internal member forces than can be found using only the equations of static equilibrium. To solve such problems, the force method combines equilibrium conditions with compatibility of deformations. A statically indeterminate structure has more unknown reactions or internal forces than available equilibrium equations. The force method addresses this by identifying redundant forces reactions or internal forces that, if removed, would make the structure statically determinate, for example, a fixed end beam with a support removed. Example: if a fixed end beam is the primary structure, removing one support creates a simply supported beam. The redundant forces are removed or released, transforming the indeterminate structure into a determinate primary structure. Compatibility equations ensure that the deformations in the original structure are consistent with the constraints imposed by the redundant forces. For instance, if a support is removed, a compatibility equation would state that the displacement at that location must be 0 or consistent with the original support condition. These equations relate the displacements in the primary structure due to the applied loads to the displacements caused by the unknown redundant forces. The compatibility equations are solved simultaneously to determine the values of the redundant forces. Once the redundant forces are known, they are applied to the primary structure to determine all internal forces and reactions in the original statically indeterminate structure. Displacements in the original structure can then be calculated using methods like virtual work or the principle of superposition. Tutorial 1. The steel rod shown in figure 4.8 has a diameter of 10 millimeters. It is fixed to the wall at a RIS, and before it is loaded, there is a gap of 0.2 millimeters between the wall at B and the rod. Determine the reactions at A and B if the rod is subjected to an axial force of P equals 20 kilonewtons. Neglect the size of collar at C. Take S steel equals 200 GPa steel. Tutorial 2. The assembly consists of an aluminium rod, AB, and a steel rod, BC, each having a diameter of 12 millimeters. If the rod is subjected to the axial loadings at A and at the coupling B, compute the displacement of the coupling B and the end. A, the unstretched length of each segment, is shown in the figure 4.10. Neglect the size of the connections at B and C, and assume that they are rigid. Steel 200 GPa, E aluminum equals 70 G Pascal.